Hey kids, Charlie Busso here. We're going to be doing page 8 in the bonding notes. Started here with number 53. All right, it says draw the structural diagram for HCl. Now we just drew the electron dot diagram for HCl, and really quick, it looks like this again. 7 dots around chlorine in red, 1 around hydrogen. They're going to share 1 pair of electrons in the middle. Now look what it says here. This is going to make our lives a lot easier, our lives. A dash equals a pair of electrons being shared. This is a Lewis dot diagram, and it's perfectly fine. But honestly, after enough practice, you should just have this in your head. You don't need to draw these dots forever. You can just know that they're there. So in order to draw HCl, you know that hydrogen has 1 dot and chlorine has 7 dots, and they fit together in a 1-to-1 ratio because they're going to share 1 pair of electrons and make what's called a single polar covalent bond. Now, as a shortcut, we can just do this, HCl. And that dash in the middle means they're sharing 1 pair of electrons. 1 dash equals 1 pair of electrons being shared in a bond. We don't have to draw all the other dots around chlorine. They're there. They're in your head, though. You don't have to draw everything anymore. You just know they're there. It's kind of like when you give somebody directions. Somebody says, how do I don't know, how do I get to New York City? Well, a lot of the directions are get on Route 17 East and just go all the way to exit 116 and then take the New York State Thruway south. You don't have to tell them every turn on Route 17 or where the bathrooms or Dunkin' Donuts are. They just follow the road. You can just follow your brain. You don't have to show every detail. You just know that that's that. All right, Lewis dot diagram and structural diagram for ammonia. Ammonia has 5 valence electrons, which I'm going to open up this way because it's got to make bonds to 3 hydrogens. I'm going to put a hydrogen over here, a hydrogen over here, and a hydrogen over here. Now, I could simplify that this way. N bonds to H, H, and H. No dots. Here's dots. Here, the dots are in my head. I know there's 2 dots up on top. I know each dash means they're sharing 1 pair of electrons. I know that the nitrogen is going to borrow 3 electrons and give itself an octet. I know each hydrogen is going to borrow 1 electron back and get full baby little sized orbitals. CH4 methane, I'm going to use the space over here. Carbon is going to have 4 valence electrons, which I'm going to show there in red. Then I'm going to put a hydrogen over here, a hydrogen over here, a hydrogen over here, and a hydrogen over here. I know all that. What I also know is I can do this. And these 2 diagrams say the same thing. This is the beginner. This is how you learn what this means. This works because each dash is a single bond, 1 pair of electrons. See this 2 electrons right here? That's what that bond is right there. Those are connected. Each pair of electrons is a dash. Now, CH4 and NH3 and HCl are all going to be single polar covalent bonds. Here's 1 single polar covalent bond. Here's 3 single polar covalent bonds. Here's 4 single polar covalent bonds. Now, because we can check their electronegativity values, we could potentially say which of these bonds is the most polar or which is the least polar, because we can check what's called the electronegativity difference. So we're going to fill in this chart and talk about this, and this will make good sense to you quick. First molecule I gave you is called hydrogen, H2. Atom number 1 is H, right? Atom number 2 is H, and the difference between them is 0. And this is what's called the structural diagram, right? PCl3, there's phosphorus and there's chlorine. I need the electronegativity value, so I'm going to open up table S, and I'm going to look here. Phosphorus has a 2.2, and chlorine has a 3.2. So we have 2.2 and 3.2. What's the difference between these two numbers? 1.0. Now, what is the structural diagram for PCl3? Phosphorus has 5 valence electrons, and each chlorine has 7, so it's going to bond this way. Look at this. I'm going to go up this time. It doesn't matter. There's just 3. That would mean there's 2 dots down here. We can't do the polarity rank yet, but this is very polar, and this is non-polar. So we got to do all 5 of them before we can do this. OF2, oxygen and fluorine. You know what's funny? What's another name for this? Off. No, that's not true. It's just a joke. Oxygen has a 3.4 and fluorine has a 4.0. What's the difference between these two numbers? 0.6. Now, how would we draw this? OF2. Well, the O is going to be in the middle, and it's going to bond to a fluorine over here and a fluorine over here, and it's also going to be bent, right? Oxygen likes to make bent molecules like water also. HBr. H and Br. H has a 2.2, and bromine, I can't remember them always, 3.0. The difference here is 0.8. Now this is, hydrogen has 1 dot, and bromine has 7, so it's going to go together like this, HBr. 1 single pair of electrons bonded together, and it's going to be a polar bond. Now H and I, H is 2.2, and iodine, when we look up iodine, is 2.7. So the difference here is 0.5. And H is going to bond to I like that with a single bond. There's 1 dot for hydrogen, 7 for iodine, and they go together in a 1-to-1 ratio. Now, how do we know which of these bonds is the most polar to the least polar? Well, the greater the difference, the most polar. So this is the most polar bond. This would be the second most polar. This would be the third most polar. This is the fourth most polar. And this one actually is non-polar. So in rank, this would be 1, 2, 3, 4, and last 5. The greater the difference in electronegativity, the more polar the bond. So when phosphorus and chlorine are making this bond, because the chlorine has a much higher electronegativity than the phosphorus, when they share electrons here, what happens is the chlorine side gets the electrons most of the time, leaving the phosphorus side more positive most of the time. When H and Br come together, Br has a much greater electronegativity, so the Br side is going to be negative, and the hydrogen is going to be more positive. For OF2, fluorine is much greater. Fluorine is the highest electronegativity. So the fluorines are going to be negative, and the oxygen side, relatively speaking, is going to be positive because it's going to lose its electrons to fluorine. Here, the iodine is going to be negative, and the hydrogen is going to be positive. And for the top one, they're going to share their electrons perfectly evenly. There's going to be no difference. This is a non-polar bond. But because iodine, for instance, gets the electrons more because it has a higher electronegativity, the iodine side is going to be slightly more negative than the positive. But they're all different, right? The greater the difference, the more polar, and the less difference, the less polar the bond.